This was the slide that we ended with last class. What we ended with last class was introducing something called orbital notation, where instead of the board diagram that you just did for homework, again, electrons circling around the nucleus, we were showing these up and down arrows. And we had to abide by two rules that I wrote up on the board as well. Again, so I wanted to start today by just reviewing that with you a little bit. Here's the start of that orbital notation. One of the things that I mentioned last class is that every atom starts the same way. We have a nucleus, and then we have inner electrons in that first energy level, and then we build out from there. So every element starts in the upper left-hand corner of your periodic table in the 1s. When we drew one arrow up, that first arrow is for the very first electron in the innermost part of the electron orbits. That would be the hydrogen electron. Then the second one is helium. Then we move down to 2s and 2p, all the way to 3s. Again, if I go back to your periodic table, here's 1s, here's 2s, and 2p. 3s gets us through the element of magnesium. If I want to get to potassium, which is what the problem was that we ended with, was from there, how we fill the 3p. One of the things we talked about last time is the 3p has three separate rooms, suborbitals, if you will. We have to fill them one room at a time. So for example, when I draw an up arrow here, if I counted my number of arrows, 2, 4, 10, 13, 13th element on the periodic table is aluminum. If I would stop right here, getting rid of this 4s part, if I would stop right here, this would be the orbital notation for aluminum. And that's where, again, all three of us chemistry teachers understand that when we show this to you guys early on, we're kind of looking at this like, what in the world are you doing, man? You're drawing arrows? What does this have to do with an atom? We're trying to acknowledge that that board diagram that we drew in the homework is not what an atom looks like. And yet that's what everyone wants to draw. We're simply trying to say, here is the electrons and where they're located. And there are applications to this that we can use later on throughout the course of this year. The problem is we can't do those applications until we first just show you all this information. Remember, if I need to add another electron, I add it in the next room over. I don't double up electrons until I have to. So I do up arrows first. Now, once I've filled each suborbital with one electron, a down arrow. This is the fourth element, or fourth electron rather, 1, 2, 3, 4 in the 3p. That would correspond to sulfur. Then there's chlorine, and there's argon. When you get to the end of a line, you move down to the next line, the fourth energy level, the fourth row across, and the S. I draw an arrow, and I'd be done with that one. This is what we ended with last class, although it was kind of quick to the end of last class. We are not trying to draw an atom like you tried to do on the homework with the board diagrams. We acknowledge that it just doesn't work. Instead, what we're trying to do is label what electrons do we have and where are they located. That's the ultimate goal. Again, a board diagram shows you these nice, cute shells like planets around the sun. That's just not how it works. There are 19 arrows up on the board right now because there's 19 electrons for potassium. Now, at some point, you are going to have to do elements even at the bottom of the periodic table. So we have to do elements that are way down here in the f orbital and then the lower d orbital. That's when things get a little bit tricky. I like to use kind of the analogy of the three ways I'm showing you how to represent electrons today. It's like giving you directions. Orbital notation gives you the most exact directions possible. So if you've ever had someone handwrite you directions of how to get from point A to point B, and not only are they telling you how far you have to go and what road you have to turn on, but they'll say things like, well, hey, there's a Walgreens at this corner. That's where you turn for this one. Oh, and then there's this farm with the silo that's half broken. That's where you turn left on this one. Orbital notation gives you a lot of information. I understand right now we don't see that information because it's early in the process, but it gives us a lot of information. Quite frankly, you don't always need that much information. So what we have to go over today is, yeah, we have to practice this, but then we're going to go over other ways to show how electrons are organized as well. And the first way that we're going to do that is called electron configuration. Now, I don't know if you even have to write down this definition of show what orbitals and energy levels will fill to get to the element. Instead, what I'm going to do is I'm going to show you the electron configuration for potassium. In other words, your notes today, I'm showing you the orbital notation for potassium. Now I'm going to show you the electron configuration for potassium. By showing you the same element, we can compare how the two are different from one another and how they're similar to one another. If orbital notation is the most exact directions to get from point A to point B, if we're using kind of a I'm traveling somewhere analogy, electron configuration is going to simplify it a little bit. I don't want to bring 3 pages of notes of how to get from here to the Pfizer Forum in Milwaukee if I only need to have like 1 sheet of paper or half a sheet of paper instead. So I'm going to go back to Smart Notebook, then I'm going to start drawing out the electron configuration. Hopefully, as you are writing this down with me, you keep this in mind. And actually, I'm just going to extend the page so we can see. If you know orbital notation, you'll know electron configuration. So maybe you don't appreciate it, but I actually showed you the hardest thing that we're going to do first. And now we're going to make it simple. Orbital notation wanted to show where electrons are located. The 1s, the 2p, the 4s, whatever it might be. It wanted to show the spin of the electrons, up arrows, down arrows. It wanted to show which suborbital they were in. Electron configuration doesn't care about that. Electron configuration just says, hey, where are the electrons? So, if I'm going to do the electron configuration for potassium, remember here is the 1s. We always start in the front. 1s2. 1 is the energy level, s is the orbital, 2, that's the number of electrons. After 1s2 would come 2s2. I'm using a superscript for the number of electrons. Okay, folks, what comes after 2s2? 2p6. Because after 2s, I'm in the p orbital. How many electrons in the p orbital? 6. What comes after 2p6? Drop 3s2. After 3s2, Jackson. 3p6. Tyler, what do we end with then? 4s1. Takes up a lot less space, that's for sure. Takes up less time. Again, sometimes knowing the suborbitals, knowing the spin of the electrons is important. So that's why we need orbital notation. But quite frankly, it's not always important. Sometimes we just need an abbreviated version of our directions, if you will. Again, these superscripts, these numbers up above. So again, when I look, the 2, the 2, the 6, the 2, the 6, the 1, they should all add up to 19 because there's 19 electrons. How many electrons do I have in the third energy level? Well, between the S and the P, I have 2 plus 6 is 8. How many do I have in the fourth? Well, in the S, I have 1. So electron configuration is a shorter version of this. But it still gives us information. Most students prefer electron configuration over orbital notation because there's less to write. Correct? Well, if you like that, then my gift to you is a shorter version than that. The third way we're going to teach you how to show electrons right now is called the shorthand notation. The key to the shorthand notation is it uses the previous noble gas. Now, you might not know what that means yet, so that's what I will go over here in a minute. So I'll let you jot this down. And then eventually when I tell you what a noble gas is, we will write the shorthand notation for potassium. Later in this unit, we are going to go over what's called families of the periodic table. Learning about electrons will teach us that columns of the periodic table, so the up and down part, a lot of elements in a column have similar behavior. And if they have similar behavior, we refer to them as a family of the periodic table. So first off, if I go back to the periodic table for a second, noble gases are the far right-hand column of the periodic table. Remember how when we do electron configuration and orbital notation, we go left to right. And as you get to the end of a line, so if I start at the second energy level, and if I get to the end of the line, now I move down to the next line. So just like you're reading a book, left to right, top to bottom. The very far right-hand side is our benchmark, kind of. It is the end of an energy level. So that's why, in shorthand notation, we first figure out where is that. So again, if I make this a little bit larger, we are going to write the shorthand notation for potassium. Potassium is element number 19. Again, I have the cursor over it right now. Shorthand notation, if I use my analogy of directions, again, if we're going to the new Bucks Arena, orbital notation gives you every single direction and it's just very tedious. It gives you as much information as possible. Electron configuration, let's shorten it up a little bit. Hey, get on the interstate, take the Jackson exit in Milwaukee. You know, it abbreviates it a little bit. Take a right on Wells. Orbital notation assumes that you know how to get basically from one city to another, and it just has to give you, like, here's the little leftover. So I don't have to tell you how to get to Milwaukee. I can just say, hey, go to Milwaukee is step number 1. Then I can tell you the last couple of things. That's really what orbital notation is. Electron configuration shorthand. If I want to write the shorthand notation for potassium, I need to go to the previous end of a line, because that's kind of a benchmark. The previous noble gas is argon. So here's what I can do. If this is my electron configuration, shorthand notation for potassium would start with the previous noble gas. And it has to be the previous noble gas. It can't be any other element. We always stop at the end of a line. By putting argon in brackets, it's the same as me writing 1s2, 2s2, 2p6, 3s2, 3p6. Now all I have to do is write the ending. Because I'm telling you, hey, first off, we have to get through the argon line. And now 4s1. Doesn't give you a lot of information. However, this shows you the outermost electrons, or in this case, outermost electron. One of the things that you're going to be learning after our quiz, so when we get into November, is outer electrons play an important part in how things bond together. To move from an individual atom to a compound, like H2O, NaCl, it all deals with outer electrons. So sometimes that's all we care about. In black is orbital notation, what I showed you last class. A lot of information. Again, maybe we're not aware of yet of what we can use it for, but it gives you a lot of stuff. In blue is an abbreviated version of orbital notation. All it's showing is here's where the electrons are located. And in green is the shortest version, the noble gas version, the shorthand notation, which basically says, hey, argon's at the end of the third line. Let's just pretend that you wrote all that down. And now here's the leftover. These three ways to represent electrons is what we need to be able to study and be able to demonstrate. Before we practice this a little bit more, I want to go over one more slide with you, however. You might have noticed on the homework, I gave you a couple of elements that had charges to them. An ion is an atom that has a charge. Atoms will have a charge either because they gained or lost electrons. A term that might help you out in what we are doing is called isoelectronic. It means having the same number of electrons. For example, K+1 and argon both have 18 electrons. What I'd like to do to finish up notes, because the notes part is done, is I want to go over two more examples just kind of off the top of my head. Show them to you, and then give you guys time to work on this for a little bit. Again, I know introduced it on Thursday, and it was a long drudging through notes process, and then you take a full weekend off, and you would come back first thing Monday morning, and I'm asking you, hey, we got to know how to do this. I get it. It's not easy, and again, it's arrows. It's weird. But it's a skill that we have to learn how to do. And the sooner we can figure it out, the sooner we can start doing applications with it. So, I did all of these problems based on potassium in the 4th energy level. Notice that there's S and P involved in this. Let's do something that's a little bit more difficult to wrap things up. Because here's the nice thing about this, is if I can do something at the bottom of the periodic table, every element builds up the same way. So if you can do element 100, you can do any element before that. I don't want to do element 100, by the way, right now. I want to do something a little bit smaller than that. So, looking at the periodic table, how about we do uranium, element 92. Okay. I'm going to do all three versions. And then let's give you guys time to work and practice. By the way, I don't think we're ever going to do orbital notation, the up and down arrows with uranium, because you'd be writing forever. And we don't want to test you on having to write down forever. That being said, if I can show you orbital notation for uranium, element number 92, you should be able to do every element prior to that. Okay. Every element starts the same. Innermost electrons, 1s. Can I fast forward this process all the way through calcium? Element number 20. So I'm just going to start writing. You can follow along, but really nothing has changed until we get to that d orbital, which is kind of goofy. So 1s up and down, 2s up and down. Again, with the p, I fill each suborbital with 1 before I double up. If you have more room off to the right, feel free to do that, but so far, I've gotten through 3s2, which is magnesium. That gets me through argon. That gets me through calcium. Again, look at your notes. All I did was take potassium and I added 1 electron. Every time it builds up the same way. If you treat this less of, man, I got to figure out what those arrows mean, and more of, hey, this is just a pattern. And all you're asking me to do is make a pattern with arrows. I might not know what the arrows mean, but I can figure out a pattern. That's great. I will take that any day of the week. But now, as we get to 4s2, to calcium, this is where the periodic table gets weird. Between calcium and scandium, elements 20 and 21 on your periodic table, I probably had you write down a big number 3, right? I had that d orbital next to Sulfan test last class. 5 suborbitals that make it up. The d orbital is so big that even though it starts in the 4th energy level, it overlaps with the 3rd energy level. When we get to the middle of the periodic table, that's when things get a little weird. But the d orbital is huge. It's kind of like if you ever went to a Packer football game, you don't have individual seats like you would at a Brewer game. You have a bleacher seat, and there's numbers on them. So I don't know if you guys have ever been to that, noticed that or not. If you have someone who is really, really large, they will sometimes not only sit on their number, but they will overlap with the number right next to them. And sometimes you get these rows across that you're also squished together because there's too many big people in that row. They're overlapping. The d orbital is like that, where it's just a really large orbital. So it tries to be in the 4th energy level right after 4s, but it's so big it actually spills over into the previous one instead. So that's why we have to label it 3d. In your notes, we showed how many suborbitals there were. There are 5 suborbitals in the d. 1, 2, 3, 4, 5. Just like there's 3 suborbitals in the p, then there's 5 in the d. My first arrow up would be for scandium, which, if I were to stop right now, this would be the answer for scandium. Some students will ask, do I have to draw in those empty suborbitals, those 4 extra dashes? Yes, you do. Once you write down 3d, you have to show that there are 5 suborbitals in the 3d, whether or not they're filled. After scandium comes titanium, then vanadium, then chromium, then manganese. When each suborbital is filled with 1, now we can double up, opposite spin though. And I'll just fill in my iron through zinc. Okay? We are at zinc right now, element 30. So if I ever asked you to write down the orbital notation for zinc, right there's the answer. After the 3d is filled, we get back into the p orbital. Remember those last 6 columns in the periodic table? And look how nice Kinsey has this colors outline thing going on here. So we are right there. It might be helpful if you didn't write it down between zinc and gallium to note that we jump back up to the 4th energy level. So now we are in 4p. And if I fill in those 6 arrows for 4p, that gets me all the way to krypton. Okay, ready? Krypton is element number 36. We're trying to get to element 92. We're not even halfway there. Rubidium and strontium are in the 5s. Up and down. Lydia, after 5s, what comes next? So 5s was where strontium element 38 is. We need to get to yttrium now, element 39. After the S comes what, if we're reading left to right? The D. And what number do we put after 5s? Or after, right before the D, I guess. Maybe I'm not saying it right. Remember how we went from 4s to 3d? We go from 5s to 4d. That has to be completely filled. 4D being completely filled gives me all the way to cadmium, element number 48. Now we are over halfway there. But in order to get to number 49, indium, we have to jump back up from 5s to 5p. I'm sorry, from 4D to 5p. And that will be completely filled. That gets us to xenon, element 54. Means after 5p comes 6s. And after 6s, I have 2 electrons there. That gets me to barium, element 56. So once again, anything barium earlier, we've actually written out. Just take away electrons. But this is where it's going to get weird. After barium is element number 57. Element 57 shows up right here on the periodic table. It's in the d orbital, and you probably have a big number 5 right next to it, correct? Okay, so I'm going to start with that. 5d. Once I write down 5d, I have to write down my 5 suborbitals. There's my up arrow. I don't know about you, but when I was taught counting, after element 57 should come element 58, not element 72. When you look at your periodic table, right next to element 57, La, the next one over is element 72, hafnium. This is where your periodic table might have a star right above the La. Because after you start to fill the 5d, you need to move down to element 58, which is in the f orbital. So again, things are getting a little weird, but as we get into this middle part of the periodic table, things get weird. You should have a number 4 written next to cerium, I hope. So before I can fill in the rest of that 5d, I have to fill in my 4f. The f has 7 suborbitals. 1, 2, 3, 4, 5, 6, 7. So if I have to completely fill the 4f, because I have to go through all those elements, up, 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 down, 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 down. If I were to stop right there, I would have 71 arrows on the board corresponding to element 71 in the periodic table. And we're getting close now to uranium, but we're not quite there. After 71, now comes 72. And we could fill all of that D in if we want to. So I'm now going to go back up to my 5D and finish filling that in. We're at mercury, element 80. That was 5D. After the D comes the p orbital. And the p, we jump back up to the 6th energy level. So now I have 6p. And that will be completely filled as well. That gets me to radon, element number 86. Our goal was uranium, element number 92. We're almost there. Although I have to extend the page again. Radon, element number 86. We get to the end of the line. We have to start the new line. Hopefully next to francium, you have written down a big number 7. Because that's the start of the 7th energy level. First arrow up is for francium, next arrow down is for radium. After radium, which is element number 88, we have to do element 89, which is AC. That is in the 6D. Again, if I were to stop right there, I'd be at element 89. Actinium. After element 89, there probably is a double star above your AC, indicating you need to jump down to the 5F. And that's where this is finally going to get to a finish here. Five F should have 7 suborbitals. 1, 2, 3, 4, 5, 6, 7. And if I look on the periodic table, uranium is the 1, 2, 3rd element in that, which means it should have 3 electrons. 1, 2, 3. We would never ask you to do this on a quiz because it takes up way too much paper and it takes way too much time. Plus, we never work with uranium because it's radioactive. But by doing all of this, you should be able to do any element prior to this. Plus, we could do the shorter versions of this. So this is where you guys are going to start to chip in, all right? We're going to write the longhand version instead of the arrow version. So, you might want to refer back to what you've written down as we fill this out. I'll start us off. Starts as 1s2. Alec, what comes next? 2s2. Remember, you can look at your periodic table, or you can look at what you just drew out for orbital notation. All orbital notation does versus electron configuration. In electron configuration, I still write down the energy level, 2, the orbital s, but then instead of drawing arrows, I just say how many arrows were there. So Alyssa, after 2s2 comes 2p6. Again, don't be intimidated by it. Think of it as a pattern. Brooke, you think you got this next one? Or should we go cat? 3s2, yeah. Cat. 3p6. Charlie M.
4s2.
Charlie S. Nobody fill up the D? Not 8.
Oh.
3d10. And I'm running out of room, so I'm just going to keep on moving over now. Caden, after 3d10 comes Gene, 4p6. Again, all we're doing is taking our orbital notation and rewriting it. Jackson, after 4p6? 5s2. Grant? 4d10. Emily? 5p6. Cole? 6s2. Okay, I'm going to chip in here for a second. 6s2 just got us to barium. Element number 56, on the periodic table. When we get to the D and the F is when things get a little tricky again. So here's how I would approach this. After 6s2, I would say 5d1. Because that gets me to LA. Now we need to get down to element 58 through. So Kinsey, after 5d1, what would I write? 4f14. After 4f14, I finished through element 71, right here. Now I can go back and finish the rest of this. So what I'm going to do is I'm now just going to go back up to my 5d1 and call it 5d10. Now if I were to finish in the middle of that 5d, I would just say like 5d5 instead. All right, Lydia, we got through 5d10, which is mercury. What happens after 5d10? 6p6. By the way, some students ask me, does it matter the order we do this in? If you were to happen to flip your D and your F, I could care less. I have no problem with that at all. We usually teach how to read the periodic table left to right, top to bottom. So that's the easiest way that we do it. It's not the only way to do it, but we feel that's the easiest way to do it. We just got through 6P6. Mary Eileen, after that? 7S2. Mike? 6D1. Kim? 5F3. Longhand notation. Let's finish up with shorthand notation. Uranium is element number 92 on the periodic table. Tyler, what is the previous noble gas? The previous element that's on the far right-hand side. The end of a line. From element 92, work backwards. Previous, so smaller number than 92. Test. Radon. Going backwards to 92, 91, 90, 89, 88, 87, 86 is radon. So, in brackets, we write down Rn. And all we've done is written everything up to this right here. That's the nice thing about shorthand notation, especially for larger elements. All I have to do is finish off the rest. 7S2, 6D1, 5F3.